Yeah.
Yeah.
Was it computing the correlation or just interpreting it?
Hold on. Dr. Schaefer's homework. Okay, so chapter 6 is homework and it was question 4.
Yeah. How does it go?
It basically just gives you, okay, maybe it says, here are several scatter plots, and then it just gives you like the 0.77 and a negative 0.487 and a negative 977 and then a 0.006.
Oh,
And then it says
gotcha.
match each scatter plot with its calculated correlation.
I
But
gotcha.
I would struggle to match that.
So I think the major idea with that one is you want to look for the graphs where there's a positive direction
Yeah,
and give it the positive value for the correlation.
and I knew that, but one of my graphs is like a U.
That
with
would
all
have
the
no
scans.
correlation. Yeah, that would be the
But-
case
but
where,
then I still have to match the number.
Yeah, so
Oh,
it says
gotcha.
correlation, so that was like 0.006.
Yeah,
I see. So maybe we should try that as a class. Would that help out?
yeah. that would be
Okay, let's
great.
take a look at that. So you said it was problem number 5, section, chapter 6.
Question 5.
Okay, welcome back, folks. We're starting off with a question from the class. Thanks for asking that one. Always takes a bit to actually load into the
That's okay.
homework, so we get a little bit of a mental break right when we start. Not just the internet. This is like really hacked together software. It just barely functions.
Well, do you know if they're supposed to, I've heard rumors they're gonna switch to Canvas
They are.
spring semester?
They don't know when, but they're trying to. It's a good chance that they keep pushing it back.
Trying to.
Yeah. So it may be next semester, but I highly doubt it. Probably more likely fall 2025.
Okay.
But even then, they could push that back further. Oh, I need to go. Here's where they are. And it's turning into a long list, but we're almost at midterm, so that makes sense. And it should be that one there.
Yeah.
Gotcha. Let's take a look at this one. This will be a good activity just for the class. Looks like this is a challenging one. Let me move some windows around. And you can kind of scale these around if it kind of helps with your viewing screen. Okay, so it says here are several scatter plots. The calculated correlations are 0.77, negative 0.487. That one's a really, really strong one.
Yeah.
Negative 0.977. Let's identify that one right away. Anyone see what that one should associate with? Good call. If it's so close to -1, it means the points are practically on a line, so that one's got to be B. So that means down here we would type in negative 0.977. And this is touchy because if I mess up there and accidentally put an 8, I bet I lose the whole question. So careful with that.
Also, if you lose it, if you equal the negative or the 0.
Oh,
I don't know
wow.
about the 0. Did you try it with
It's
the
a
0?
0 too.
Is it the 0?
Also,
Try it with a 0 just to be safe. It looks like is a good call on that one. So other one is 0.006. I think we can find one for that as well. Anyone see what that one ought to go along with?
would that one be A, it's the weakest?
Probably A, although kind of an oddball problem. Really shouldn't even calculate correlation on that one. Let's see if we can identify A just by elimination. So let's go through these again. So negative 0.487, that's going to be the scatter plot with a downward direction like that one, but a whole lot more spread. It's got to be C. Would you all agree with that one? So C is in negative direction, a lot of spread. So we'll go over here and say for C, negative 0.487. So that takes care of that one. And we took care of that one. That one we're thinking is part A, but let's take a look at 0.777. It's got to go in the positive direction, not as strong as this one. Looks like D. Absolutely would agree with that one. By elimination, we're starting to get these pretty quickly. So on D, we're giving that one a positive correlation, 0. Once I find the home row, 0. I think it's this glove that makes typing weird, 0.777. So by elimination, again, you wouldn't want to calculate correlation at all in that thing, but if you did, looks like it comes out as a 0.006. So that would be my best guess on first look at this one. How's that look to folks? Any changes you'd want to make? Okay, let's hit check answer. And yeah, they're happy with that one. Any other questions with how this one went?
I just didn't understand it at first. Like,
Gotcha.
what exactly we're asking, so.
Yeah, we didn't do problems exactly like that one. Ours was slightly different where we were just saying R bigger than 0, R less than 0. Here it was more focusing on which ones actually had the stronger or weaker correlation. So a little bit more in depth for this one. Yeah, educated guesses. Yeah, exactly. Well, other questions at the moment, folks, with this one, or other questions to start us out today? Okay, thanks for bringing that question. I always call for questions, but keep in mind, you're always welcome to ask them. I'd love to take questions at the start of class. And if something just comes up in the middle of class, we could finish up our problem and take a look at that question as well. But let's close this up. Well, maybe just minimize it for the moment. And here's where we're at so far with the announcements. Once I get that, there we go. I like these boxes because I can put the annotation right where it was supposed to be. There it is. So here's our announcements for the day. Nothing too major for the current week that we're in, other than quiz 5 is due today, and we have our new quiz number 6 posted. As far as quiz 5 and quiz 6 go, those are going to be really huge for the upcoming exam 2. Those are quizzes where we use the calculator the most, using statistical functions. And so quiz 5, that's pretty much handling section 5.4, and quiz 6 is handling the chapter 6 content. If you can get through both quiz 5 and quiz 6 using your calculator, then you're all set up for the exam, I would say. So I'd say get working on that one early. It's pretty much just studying for the exam, working on the quiz. Other things I have on my announcements are, well, this is kind of just a doodle, but we're almost at the halfway mark. And again, this is going to be just a normal midterm week for us. We will take questions on Thursday relative to the exam 2. So that'll be reminded once we get closer to that date. As far as exam 2 goes, this is now the firm content. We might have got chapter 7 on there, but I feel like chapter 6 and chapter 7 are technical enough. It does make sense to split them across exam 2, exam 3. So exam 2 is officially ending at chapter 6, starting on chapter 3. And like before, I can't ask every single question on here. So I'm going to try to get a representative spread of questions through these sections. There is one unusual section though. Section 5.3, that was using the 68, 95, 99.7 rule of thumb, and it's still an important rule of thumb, but the major purpose of section 5.3 was to give us a mental picture, so when we're in section 5.4, when we go to use the calculator, we can decide if our answers are even reasonable in the first place and understand how to organize the information. So that means I'm not going to ask a question directly out of section 5.3. It's a good one to review a little bit, but we're going to emphasize 5.4 and definitely ask the questions out of that one. So this was kind of like a preview to the calculator, essentially. Sure, absolutely.
On question 6, on the same one.
Yeah.
It says, how do you plot the points? And that's fine, but then it says, what is the correlation coefficient for the data? How do I don't remember how to figure that out.
Oh, in your calculator,
Yeah.
to get your correlation coefficient, let me see if I have data inputted. Let's see, go stat. And we've got some data inside there.
Yeah.
So to get your correlation coefficient, hit the stat button, move over to calculate, and down arrow to option number 8. So that gives you what you're doing in chapter 7, as well as the chapter 6 correlation coefficient R. If your calculator doesn't produce that, then you have to go through the file that where you turn diagnostic
I couldn't
on.
remember how to do that, so thank you.
Yeah, absolutely. Other questions at the moment? Okay, so let's see, back to this right here, I guess this is our full list of announcements we've got going on so far. This in content here, the 2 bullet points, exactly the same as before. We're not going to change that from exam to exam, but it's just helpful to reiterate it, I guess. And I just put a quick note here. I'm going to have the exam 2 review questions posted over the weekend, but I consider Friday the weekend. That's a weird thing I usually do. I never actually teach on Friday. I'm going to try to actually get it done on Friday, but Saturday would be the latest. Well, any other questions about the announcements or whatsoever? Okay, let's start our work for today then. We're on the last example of chapter 7 here, but I posted an extra example as well, so that way we're not going too fast. I think this is a pretty technical section. It's worth to take our time on it. So first problem of the day is the last example on chapter 7 notes, but then we're going to go to the extra example below. And this is how this problem goes. It's kind of a rough problem, but this happens sometimes in statistics where you just are faced with a wall of text. That's a lot of reading to get through. First job is to start absorbing the context. And if this was a real, say, like quiz problem, I'd probably want to read it a couple times, exam problem as well. But let's start here. It says the authors of the paper, Statistical Methods for Assessing Agreement Between 2 Methods of Clinical Measurement. So that's one heck of a title. It was posted in the International Nursing Studies in 2010, so this is pretty recent data. And they compared 2 different instruments for measuring a person's ability to breathe out air. They also go on to say the measurement is helpful in diagnosing various lung disorders. So here are the 2 instruments we're looking at. The 2 instruments were called a right peak flow meter and a mini right peak flow meter. I get it says that's measuring a person's ability to breathe out fresh air. Sounds like the FEV data that we were looking at earlier. But this is kind of a fun thing to do in Microsoft Word. If you see stuff weird here, highlight it, right click on it, and you can go to search. Helps to be curious because if you don't understand the context, now it's way, way harder to get through the problem. And this is what it looks like. Yeah, it's pretty much the FEV problem. There's different kinds of these devices, but usually you take a full breath of air, blow through one end of the nozzle, and it measures how much liters you moved in that one full breath of air that you pulled in. So there's a bit of a drama here. There's the right peak flow meter, and there's the mini right peak flow meter. We wonder which one's more accurate, for example. They go on to say, 10 people participated in the study, and for each person, airflow was measured once using the right meter and once using the mini right meter. And here's the data that they have. So the mini right meter might not be the best one to use. It's a smaller device. The right meter here is probably the one that you'd be thinking of as the more accurate one. Looking at the data through here, there is disagreement, right? If we look at, say, subject 4, just randomly selecting them, that one's pretty close, but the very next subject had a big difference. One of the things that could happen here you have to think about is maybe the person just got tired of doing the measurements after they did the first one. So hopefully they randomized which device they used first to kind of balance out the biases there. But there is some pretty strong disagreement in some of these data. Well, that's the data, and here's our part A. Part A says, suppose that the right meter is considered to provide the better measurement of airflow. So that's the gold standard then, the big one. But the mini right meter is easier to transport and use. So imagine that you're maybe working for Doctors Without Borders, something like that. That would be a good thing in your toolkit, even if it's less accurate. It goes on to say, if the 2 types of meters produce different readings, but there's a strong relationship between the 2 readings, it would be possible to use a reading from the less accurate device, the mini meter, to predict the reading that the larger meter would have given. So if there's a strong correlation between these values, even if you use the less accurate one, we might come up with a formula to translate the less accurate results to give what the more accurate device would have given. So it looks like that's what the idea is with these data so far. Any questions at the moment about the context?
Is it kind of saying that the mini right is the independent Or is it saying that they're both kind of independent, but they can correlate?
They are definitely saying that they hoping it correlates, but I agree with you. They're thinking of this as the independent one.
Because it's saying it's possible to use a reading from the mini to predict what the larger one is saying.
Exactly. That's kind of saying this is going to be thought of as the response, and this is the explanatory. Good eye on that right there. Let's highlight this. It would be possible to use a reading from the mini right meter to predict the reading from the larger right meter would have given. Definitely highlight worthy and good eye on that. That's telling us a lot about these variables. They're telling us that this one is the explanatory. I put the variable x and comma explanatory. And then this one is going to be the response, which we conflate with the variable y, comma response. Which means for x, we're going to be plugging that into L1, and for y, we're going to be plugging that into L2. So another thing that we mentioned before is I don't try to format my data in weird ways that's going to make this tricky. Most of the time when you're giving data like this, your explanatory variable should come first. But still, it pays to really watch out for this, just in case maybe a problem in the homework did something weird and actually flip the columns around. That's possible. On a quiz or exam, that'll never happen. We'll format the data with the way it makes the most sense. So it goes on to say, use the given data to find an equation to predict the right meter reading using a reading from the mini right meter. So again, they're being more explicit by saying that's the predictor variable or the explanatory variable, and this is the response variable. We'll round the values to 2 decimal places. So far, that's a lot of reading, but again, some of these more important problems in statistics just have a lot of context going along with them. Our next goal is just to import these 10 values, well, 2 sets of 10 values into the calculator. Looks like a lot of people are already making good headway there. I'll hit the stat key, enter, standard trick to wipe out the variables, contents. And now I'll get quiet as we carefully input these values. Hey, we need any additional time importing the data?
I did want to ask if
Yeah.
you have information that you want to put in the calculator and you wanted a scatter plot, do you have to go to the scatter plot and then go from stats, or can you just put the information in stats and go from there?
You can go from there. Yeah, absolutely. You can go right to the scatter plot from here or right into calculating the correlation regression line as well. Okay, it looks like we just about have all the data. Now, next step, it says, use the given data to find an equation to predict the right meter using a reading from the mini right meter. It wants just the equation, but if you're curious, let's take a look at the scatter plot because it's really fast now that the data's in. First thing I'll hit to get the scatter plot is the zoom key. And I think this is option 9, but I'm never too sure. Yeah, option 9. And this is what our data looks like. So that's actually kind of nice in a way. This is real data from the International Journal of Nursing Studies, and they are showing pretty interesting, strong correlation between the less accurate device, the mini meter, and the more accurate device, the right meter. So that's kind of nice. But what we wanted was the actual equation. So imagine you're back here on this screen, or on any screen really. Well, no. You really just need to hit the stat key, go over to calculate, go down to skip past option 4, We want option number 8, linear regression. So once we're here, hit enter on that one. And always double check this. It should go L1, L2, where we put our data. Everything looks like it's all set. Lots of enters, and you've got your equation. Also, check out the correlation. We're expecting something very strong by the scatter plot, but that is indeed really strong correlation between real world data. And it ought to be, right? If that device is a little bit biased, that's one thing, but if it's giving results that are not correlated with the major device right here, then that's probably never a good device in the very first place. So this shows that there is strong consistency between the two measurements. And now our equation is a plus bx. That's what our calculator always says. It's a little bit annoying that our author decided to go with this equation. Y hat equals b naught plus b1x. That's in the official reading. But then our calculator goes y hat equals a plus bx. I think I accidentally wrote that down at least once in the notes. But because we're usually using the calculator, not looking at the notes, that's not a bad thing to write down because that's what we're staring at right in the calculator. So our official equation goes like this. Y hat stands for the predicted value. So y hat is predicted value.
So it's not the exact line, but it's likely.
Sorry, say again?
It's not the exact line, but it's the predicted line.
Exactly, yeah. So we'll take our y hat, and it's a plus bx, but we just write in a first. That one's getting rounded to, let's see, 2 decimal places, so 120.95. Then we'll go either plus or minus. The B coefficient here is positive, so we'll go plus. It's 0.75 upon rounding, and then it multiplies x. So we've got it, folks. That's our format so far. And with our color coding from above, let me just make sure. Okay, intercept was blue, slope is green. Just want to make sure to copy that. So blue for the intercept, green for the slope. I also have blue for explanatory, green for response, but I'll try to use this a little bit less so that we're focusing mostly on the new things down here. Well, any questions at all, folks, on producing that line down below? Okay, so this content, coming up with the equation is not on exam 2, but coming up with that correlation coefficient R, that part is on exam 2. So that's the stuff we were doing in chapter 6. So at least the computations overlap a good amount. Next question they ask us then is, what would you predict for the right meter reading for a person whose mini right meter reading, sorry, it's a tongue twister, that was 500. So we're imagining someone used the mini device, which is not as accurate. The person tested at 500. I'm not sure on the unit there. We just want to know if we used the actual bigger device, the right meter, what would it have been? We don't know, but we can make a prediction using that equation right here. Any questions first, folks, before we try this one out?
What is the 3 on the alphabet, not the 3, the R? We talked about that yesterday, but I can't think of it.
That's the correlation coefficient. Yeah, and that's the thing that's being asked a lot in chapter 6, the homework questions, quiz problems as well. Other questions at the moment? Okay, so reading through this again, it says, what would you predict for the right meter reading for a person whose mini right meter reading was 500? When they gave us this 500, that's X, because they're talking about the mini right meter reading. Mini right meter reading, that's a real tongue twister. So all we do is, when this says what would you predict, that's y hat they're talking about. The value we're trying to predict, it'll be equal to 120.95 plus 0.75 multiplied by the provided value x, which was 500. So in part B, we're using the line to make predictions, and it's just a really fast computation over here. So the value given is always going to be the explanatory variable, since we're using it to make the prediction for our response. So back in the calculator, type in 120.95 plus 0.75 times 500. I got from that, and looks like there's no need to round. I'll just keep the full precision, 495.95. So that's what we would have predicted the person values would have been if they used the larger, more clunky, harder to transport device, which is more accurate. That's kind of fantastic in a way. It looks like the trouble with the mini rate meter is that it's biased. It's giving slightly higher values than it needs to. But this equation right here helps us make a good correction, and their values are still, again, pretty close. We expect that because the correlation was really high for these data. Any questions, folks, with part B? Okay, now next, part C is asking us to calculate the residual for the prediction made in part B. That's a confusing question, so let's spend some time with that. First thing I always want to do is focus on this word. When the word residual comes up, you should think of this symbol, E. That's our author's symbol for residuals. By formula, it's always going to be this, a Y value minus a Y hat value. Note, we already just calculated a Y hat value. So that value 495.95 is going to go right here in place of Y hat. The trickier thing I'd say is, how do we find the value for Y itself? Anyone see what the value should be?
Would we add up all of the?
Yeah. Let me double check. Not quite, but you're on the right track. You have to use the 500 for sure.
Y is the mean, right?
Y is not the mean, it's just an observation.
Yeah,
but-
so Y is the point.
The hint is we definitely do need to use that 500 though. So you're absolutely on the right track. When it says residual for the prediction made in part B, it was a prediction started at an X value of 500. But how do we get the Y value if we know X is 500?
Oh, we go to the table and go to the, what's 500, 476?
Exactly. If we're talking about a residual, we're working with data that is in the problem itself, one of the observations. To me, that's even worse about this kind of thing. So there's lots that happens. You have to know residual means, even if you forget the symbol, it's referring to this as a formula. But if you're talking about residual, you're always talking about something actually in your data set. So we take the 500, which gave the 476 when the data was paired. That's the actual observation we have to use in part C. Let's circle this right here because in my opinion, that's actually pretty hard. Well, the first couple times, it becomes easier with practice. So this is used for the Y value in part C. Does that make sense to folks on how that goes together? Okay, so again, residual is probably going to be the trickiest problem when we do this one on exam 3 now, because there's a lot going on. But once we find out what goes where, we just go here and say, this is equal to the value Y back over here was 476 minus what was the predicted value? The predicted value was 495.95, so that goes down here. Let's slap it with that marker there just for the help with the color coding. And now that's all we're doing right here, just forming that subtraction. So 476 minus 495.95. It gives us a residual of negative 19.95. The residual is just telling us the inaccuracy in the model itself when we give the actual data and make a prediction on the actual data. we have a value of negative 19.95. So it tells us this was a little bit higher than it should have been. That real value was lower by that amount, 19.95. What we did, folks, that's calculating a residual, but this is tricky enough. Let's actually give more of a visualization on this before we just move on to part D. So back in the calculator, if we need to visualize a residual, we just want to actually produce that scatter plot. So it's not something you have to do on a real problem, but more just for the sake of the notes to kind of see what we even calculated. So hit zoom, and then I believe it's option 9 on this one. Yes, I'll memorize that one day. Here's our scatter plot back, but we're calculating a residual, so I want to find where the X value is 500. So let's find that. You want to hit the trace key. So left, right arrows should get us to different values. And here it is, 500, and there's the Y value 476. Let's see if we can get a really quick screenshot here. It is Windows, Shift, and S. It makes your screen go dark. And then you have this little thing that you can drag around and just grab whatever you like. Then Control V will just paste in whatever that screenshot is. Turns into a really handy little toolkit. It's also the snipping tool, really, but the snipping tool has a bunch of shortcuts built in. So here's our display. One thing that's missing here is the actual equation of the regression line. It's that equation there, but I'm just going to try to graph it as if it would have been graphed on this. So let's see if we can put it in. Regression line's probably about like that. Then, coming back to what we calculated, we had at 500 a value with double check, 476. That's this value right here, 476 by that little star. Let's just put a dot on it. We also have the 495.95. That's this value just a bit above. That's the actual value that was predicted by our equation right here. And this distance is negative 19.95. It's negative because the actual value that occurred in the data is below the predicted value. If that red dot by my red dot was above the line, our residual would have been positive. So that's all that is trying to calculate, the vertical distance between your real data value and your predicted data value. Any questions, folks, with the work on the residual?
How do we word, what you said, the negative 19.95 is?
Oh, let me give a wording on that. We can say negative 19.95 equals E, just to say it's a residual, means the predicted value Y hat is larger than the observed value which was Y equals 476. And just to convey that on the notes as well, the 476 was the Y value after plugging in that 500. So even though we didn't need to do a scatter plot, it's kind of convenient sometimes to just look at your data. Even if all you're doing is giving the regression line, it can really help with tying together what in the world we even calculated in the first place. So that's kind of nice. It tells us we have a line with really high correlation going in, but not all values we get are perfect. There's always going to be a residual whenever we use the model to put in to make a prediction. Okay, questions or comments, folks, with part C? Okay, moving down through the next one, let's see what we've got going. Let me take the screenshot of just this equation. Part D looks like we're looking at slopes and intercepts. So let's give a look at part D first. Pasting the equation down below just for our easy reference. And question for the class, which number is the slope, 120.95 or 0.75? Good call. The slope here is the 0.75. It's always the thing that's multiplying x. So when it's referring to slope, we have that the slope equals 0.75 divided by 1. It looks like we made a big giant mess out of the slope, but this is a good idea to make that fraction for the sake of an interpretation. Next, on the horizontal axis, that's going to be the mini right meter reading, explanatory variable. On the vertical axis, that's just going to be the right meter reading. So we'll say on the numerator of the slope, that's the y-axis variable for y. And we'll say here that has units of right meter reading, kind of a long unit. Then going down this way on the x-axis, that's the explanatory variable, and that one was the mini right meter reading. Just trying to say it slow so I don't get tongue-tied again. Okay, so I would consider this to be a really important first step. Even if you make a mistake in the practical interpretation we're about to give, if you showed me this, then you're on the right track. You get partial credit just for writing this down, giving the units especially for the partial credit. But now, here's what the interpretation is going to look like. It always goes generically about the same. We focus on the denominator and say for, once I spell for correctly, for each additional, I'm not too sure what to call these, let's just call them points for the right meter. Each additional point in the mini right meter reading. So we're mentioning the denominator first. We're visualizing we're on some random spot on the graph right here, and the mini right meter moves over by a distance 1. Then we have to go up on this graph to get the actual predicted value again. The value we go up by is that 0.75 we have in the numerator. So we'll say the right meter increases because we have a positive slope by 0.75 points. So that's what the slope is trying to say. For each point in the mini right meter, you don't go up a full point in the real right meter, just a quarter of a point. Well, when it says using the context, it's pretty much this stuff right here. We said mini right meter, and we also said the right meter, but also for the sake of the notes, putting this all together, each time we go to write this out, the parts in black, each additional point, well, maybe not the parts in black, but this part right here is something you can say essentially every single time. Visualize whatever the unit is in the denominator going up by 1, and this variable will be x, explanatory. So in our interpretation of slope, increase the unit of the explanatory variable by 1 each and every time, and that's always a process that's going to work out. Then we have to say something about what happens to y, the response variable. It'll either go up or down, depending on whether the slope is positive or negative, and the amount it goes up or down by is just whatever is in the numerator. So that's a pretty generic format for each one of these kinds of problems. Any questions at all, folks, on writing out that interpretation?
So the numerator is always y,
Yes, absolutely.
and then not the denominator follows it.
Exactly, yes. Much like, think of also the numerator as being the vertical axis and denominator horizontal axis. Those always will tie together. Awesome. Other questions so far? Okay, now part E is suddenly really, really tricky. Part E is going to challenge us in how well do we know the context. So let's take a look at it. Okay, so it says, does it make sense to interpret the y-intercept of the least squares regression line? That's the y-intercept, the 120.95. It's a number, but when we say, does it make sense to interpret it, we're saying, does this number 120.95 actually have any relation to the problem at hand using the context? If it does, we'll give it a practical interpretation. If not, we'll have to give an explanation. How do folks feel about it? That's the y-intercept. Looking at it, can you tell if it makes sense or not just by looking at it? I don't think I could, to be honest. Here's where I would actually start. Sorry, say again? Yes, absolutely. So when it says y-intercept right here, what is the value of x at a y-intercept? Absolutely, the value of x would be 0 altogether. At a y-intercept means you're crossing the y-axis. Let's get a really quick graphic here, which means you're somewhere like here. That's a y-intercept. But the x value would be always 0. And did we ever say that here? Yeah, that highlighted part in yellow, that's the critical thing whenever you're trying to interpret a y-intercept. You're always plugging in 0 for x. So let's come back down to our problem. So at a y-intercept, x would be equal to 0. Now we have to ask ourselves, could that happen? Yeah. It possibly could happen, but I would say that's a medical emergency. The study wouldn't continue any longer. Can anyone see what the problem might be if you got a value of 0? Well, if we put 0 in, it would wipe out this, and you'd get 120.95.
0.75 divided by 0.
Oh, that would be undefined. We couldn't divide by 0 for that, yeah. But there's still trouble with this. So what makes this confusing is it's all about the context. It's not about the math at all. That's kind of unfortunate. So this is a tough problem because the context is not easy. Let's think about this again. The mini rate meter, what does it do? Let's see. Where is that? Instruments for measuring a person's ability to breathe out air. So if we got a 0 on any of these x values, it means the person is not breathing, right? That's a huge medical emergency. We should just administer CPR at that point. The experiment's off for that participant. So this is one of the cases where intercept actually doesn't make sense. The person's turning purple. We're not going to put a device up to their lips and ask them to blow out. They need help right away. These kinds of things happen a lot on these kinds of problems. So whenever you see interpret the y-intercept, it may or may not make sense. It totally just depends on the context. So let's be really careful here and say, sure, you can plug x equals 0 for the y-intercept and get a value of 120.95. Let's actually say that. The y-intercept is, our author calls this B, let me try again, B naught, the first value that occurs, equals 120.95, occurs when the reading from the mini right meter is 0. And really, two things could happen. Maybe the person is choking, having a medical emergency, or maybe the mini right meter device just broke, something like that. It's just not working, registering a value at all. So either case, we can say this is either a medical emergency. People might be screaming code blue or something like that, or the device is broken. In either case, it does not make sense to interpret the intercept because of that conflict. Again, at an intercept, you have a value 0 on the explanatory variable. And in a lot of problems, that has no actual bearing on the context. It's a nonsensical value, or something like this, where we're probably have to just stop the experiment. Something has gone terribly wrong. But any questions, folks, with interpreting the intercept on this one? Okay. Another thing to think about with this question is there's a third reason why you never want to interpret this intercept. Here's a different way to take a look at this. Let's look at our actual data. In our actual data, let's bring it down here just for a moment. None of these values ever occurred where x was 0. So that means even if we try to interpret the intercept by plugging in 0 for x and getting that value out, it still wouldn't be a value that made any sense in this problem. It would have been called extrapolation. Let's make a quick note there. Since x equals 0 is far away from all the data in the explanatory variable, using x equals 0 is extrapolation, and the result should not be trusted. I should slow down. I notice my penmanship gets a little bit wild if I try to write too fast. That's supposed to be the letter or the word should. So again, at an intercept, x is 0, but all the x values are ginormous relative to 0. The lowest one looks like it's 3, 4, 6 mainly. So anything that goes below 3, 4, 6 by a large degree is extrapolation, and we can't guarantee the model's accurate at all. That leads into the next question, but any comments or questions so far, folks? Okay, so the intercept cannot be interpreted for multiple different ways or reasons. And now it says, explain why we should not use the least squares regression line to predict a right meter reading from a mini right meter of 250. Well, we could plug 250 inside that equation, but same kind of issue here. 250 doesn't show up in this data as well, and so that would have been extrapolation. Looking at it from the view of the calculator, let's see, we have a minimum value for x. Trying to get my cursor all the way to the left. Oh, there it was. 346 was the minimum value. And so you might ask, well, what's the problem with just plugging in 250? Well, here's what the problem could be. The pattern we see in the scatter plot is not guaranteed to extend to the left forever or to the right forever, but it could. Maybe going in this direction, it goes up in that same pattern, but maybe going to the left, if we kept on putting new values, well, that's not showing up. Maybe it would have looked like this instead. There could be a whole different pattern in the data as we move far to the left. There could be reasons why the mini right meter gives us values that are going up when we have very low measurements going in. And so if we use the least squares regression line, it was modeling this way. So if we take a value that's really low, like 250, we're way out here, we'll predict down here, and yet it's plausible the data is either above or far below. We have no idea until we pull in data with measurements around 250. So again, same problem on this one. Let's say here, just for our official answer, we should not use x equals 250, since this is extrapolation. What we prefer is interpolation. Interpolation just means you're making a prediction within the extent of the x values. So any value you plug in that's between, say, 346 up to around 658, that's just the normal things we've been doing all along. Interpolation means you're inside the data range. Extrapolations mean you left the data either far to the left or far to the right. So even someone with a mini right meter of 1,000, we can't actually use that regression equation because there's no values as high as 1,000 anywhere in these data. So, well, we did it, folks. That's the conclusion of these notes. Any last questions on running through this problem? Okay, we have more problems on these topics because, if you've noticed, hope people have mentioned, it is a tricky subject. There are a lot of little nuances that go along in this kind of discussion. As far as the reading goes, just another reminder, we're only doing an introduction statistics, which means when it came to regression, we're only introducing regression, and there's a whole plethora of extra topics. If you're really curious, you can do the reading on these ones, but these are the subsections that I said you can safely skip, since we're not going into those further kind of topics. We're ending up to topics like you saw on these notes. But let's save this up. I think I saved it, but I get paranoid. Let me save it again. Let's take a look at that bonus problem. Or extra example. This is over here on the Moodle website. It's also in the folder at the very top, blank lecture notes. Looks like this one is also in the medical sciences. Slightly different situation though. Here's how it goes. We have data, number of factors, length of stay in days y. And notice on this problem, I just called it x for the first variable, y for the second column rather. That means this is definitely the explanatory variable, and that one is definitely the response. And here's how the problem goes. I didn't know about this jargon, but it's doing statistics is fun. You learn a lots of thing or two about different things. Here it says, any medical item used in the care of a hospital patients is called a factor. They have some examples. For example, factors can be intravenous tubing, intravenous fluid, needles, shave kits, bedpans, diapers, dressings, and so on. I'm sure you can imagine lots of stuff. Even code charts, they say, is a factor. So imagine you go to an ER, if you're, say, bleeding out of your arm or something like that, probably lots of factors go into your care. If you go into the ER and maybe nothing major is going on, but you just wanted to talk to a doctor, possibly nothing was used, they just had a consultation. It goes on to say, however, this is the coronary care unit, so probably lots of factors going on in this one. The coronary care unit at Bayonet Point Hospital, St. Petersburg, Florida, investigated the relationship between number of factors per patient, X, and the patient's length of stay in days Y. So we might think if there's a lot of factors involved with you, then you just have a lot going on. So probably you're going to be laid out in the hospital for even longer. At least that's the thinking. Looking at this, it looks like it does pan out. For this individual, 360 factors. Remember, this is the coronary care unit, so we're thinking people who had heart attacks and such. This person stayed in the hospital for just 6 days, 360 factors. The very next individual stayed for 5 days, but only 78 factors. Lots of variation in these data, it looks like. But when you put it in a scatter plot, there is at least a pattern going on in these data. So this question has pretty more minimal context. This is more like what you would see as an actual exam question. I'm going to try not to write out a huge set of context like on the last problem. Still, it's good to practice those because they can come up in the homework or quizzes. It says first, calculate the least squares regression line. So let's do that right away in the calculator. First thing I have to remember to do is turn it on, hit the stat key, enter to edit data, and first start deleting stuff. Hit clear, enter on L1, clear, then enter on L2. And this is the quiet part of class. Let's carefully type these in. Okay, I think we've just about all have it. Let's imagine this was a real exam question. What's the next button to hit to get that least squares regression line? 8 volunteers? Absolutely, we'll hit the stat key. And where from there next? Good call. We have to go to the calculate tab, enter. Oh, hang on, I messed it up. Let me try again. So stat, go to calculate, then go to option number 9. So down a whole bunch. And well, you know what, that could work. Usually we go for this one. Linear regression, A plus BX. You know, I honestly don't think I have ever in my whole life pressed that button 9. I'll do it on my own time later on. But this is the one that we officially would go to. You should have L1, L2, and then just hit enter from there on out. We also get high correlation, so that's pretty comforting. Didn't quite look like it with this spread here, but these kinds of axes can be a bit misleading, so that's why it's good to have an actual numerical measure. But the thing we wanted was y equals a plus bx. So we'll go either y, or oftentimes our author goes y hat. You might notice that's a good call because y hat is used in the formula for the residual. So it's good to be sure what's what by using that symbol. First, the a value goes in, and for 2 decimal places, it'd be 2.96. Then our b value is positive, but ever so slightly. So plus 0.01. And you know what? That's pretty accurate to round the two decimal places times x. So that's our model. If we put that line to the paper here, probably it looks something about like that is what I would guess. Any questions at all, folks, with what we've got so far? Okay, so with all that produced, we can now run through the problems pretty quickly down below here. But just for the sake of the graphics of doing the line, you might decide to hit zoom, number 9 for zoom stat. If the scatter plot wasn't produced, that could produce it for you. And you might decide to try to add this to the scatter plot. That seems like something a calculator should do, right? Let's see if we can make that happen. That's the y equals button. And put in here 2.96. The y equals button right here. And now what I'm entering in is just the model that we put down on paper. So 2.96 plus 0.01, and you get your x variable from right here. This is just for the sake of extra visualization. If you want to tell if you're drawing your line the way it should be, well, we should just be able to put it in the calculator and make the calculator do it. That way we can decide if we're happy with our line or if we need to tweak it a little bit. So after doing that, you should have that equation that we typed in down below. X is this button right here to the left of the stat key. It's weird because there's a whole bunch of symbols that's put in there. But if you hit X, you should get an X like that. Now next, we need to go back to our scatter plot to see if it drew the line for us. So click the zoom key, press option 9, and there it goes. There's our line. And that's a pretty interesting line. The true regression line didn't look like that at all. It actually goes like this. About like that. Looks like these 3 points here had a lot of leverage, And these 4 points up, these two right here, did not have enough to make the line adjust in that kind of way. It's actually pretty surprising. Usually we're pretty good at drawing these kinds of lines, but the true regression line is really that one there. Note, I did round to 2 decimal places, so that would affect it a little bit as well. But any questions, folks, with the more accurate line? Okay, if you'd like to do this, it's kind of a fun way to, again, just get extra information. But if you're also using your calculator to produce those scatter plots, you're definitely going to want to go back to y equals, hit clear on this. That way a random line doesn't just show up on every other scatter plot. So once you use the line, also kill it off right away and you'll be in good shape. Not something you have to do at all really in this class, but just for people like to play along in the calculator a little bit more, that's a cool option. Well, let's see how far we can get. I don't want to get too far since it looks like we're just about out of time. How about we make part B our last question of the day? Does that sound right to folks? And it's a nasty one, back to y-intercepts. Part B says, does it make sense to interpret the y-intercept of the least squares regression line? If so, give a practical interpretation. If not, explain why. Well, at a y-intercept, recall that would mean x equals 0. And, 0 is nowhere in sight here, but we could still potentially interpret it, even if it's extrapolation. So that's one thing that's a little bit tricky here. All it's asking is, would the intercept make sense? Not if it's extrapolation or not. So I'll leave it up to the class. Would it make sense to have no factors as a hospital visit?
No.
I think this one kind of is up to interpretation, right? Because this is the coronary care unit, meaning you have angina, some kind of a heart attack, or maybe you're following up on a heart attack. You have something major going on. It would probably be very, very unusual that you come into the coronary care unit with no factors. You just talk to a doctor and leave. They don't give you an IV of any kind, but maybe it could happen. Maybe it's a follow-up appointment, for example. I think this one is kind of open to interpretation. Because it's the coronary care unit, we're expecting everybody here to have a lot going on. So I think it would make sense to say, no, it doesn't make sense because everybody that goes to this hospital has a major condition. And so there's going to be lots of things like code charts, medications, needles, and all sorts of things going on in their care. Some people might also say, this is one of those problems that's open to interpretation. If you decide it does make sense to interpret the y-intercept, you would say, at 0 factors, the length of stay is about 3 days. That would be the interpretation. But again, this is one of those problems where as long as you defend your answer and it makes sense within the context, you would always get full credit. I think you could go either way on this one. Looks like most people are feeling like it doesn't make sense. Do you all still feel the same way? Okay, let's make that our official answer. Let's say here, since everyone in this hospital, or let's say in this unit, referring to the coronary care unit, has a major medical condition, we expect everyone to have many factors. So x-intercept means someone came into the hospital, this coronary care unit, with 0 factors. What could that have meant? Maybe they're just in the wrong unit. Maybe they need to go to something like the burn care unit. Maybe they just have a 3rd-degree burn on their arm, something like that. That could have been what's going on. We might say here, someone with x equals 0 factors is not in the right unit in the hospital. So let's say down below here, oh, let me fix that. It does not, it's, let's say therefore, forgot how to start this sentence. It does not make sense to interpret the intercept. Well, we did it, folks. I think part B, well, anything that has to do with dealing with the intercept or the slope, they're pretty tricky. The intercept is always more tricky because it really just forces us to think really hard about the context. And because y'all stuck out with this for so long, let's take a preview at the quiz problem as well. So on the quiz number 6, pretty much the same kind of stuff. This one is distance in meters and the record time running those races. So we have a record for the 100-meter race. This is from 2016, so it may be outdated. 10 seconds to do 100 meters. That's fantastic. It sounds like Usain Bolt did it. And it goes on to longer and longer races. You have a scatter plot like this. But let's ask the question right here now. If we produced an equation for this line, would it make sense to interpret the intercept for those data? Some say yay. Let's write down, let's go through the motions. At an intercept, x is 0, right? But what was x? It'd be distance. So that would be saying, if you interpret the intercept, you're saying that the distance of the race was 0 meters altogether. They didn't run at all. They just gave up at the moment they got to the line. So this would be a problem where it really does not make sense. Because this is the distance in meters for a race, x could never be 0. It has to be a positive quantity altogether. Does that make sense on that one? So this is one of those cases where it's less like the problem you're looking at here, where you could argue in either direction correctly. This is a case where if it's a race in meters, that just had to be positive. So this would produce a y-intercept, but the y-intercept wouldn't be meaningful for these data. Well, any last questions, folks, before we call it a night officially? Okay, well, this is definitely a good stopping point for us. We'll come back on Monday, finish off these notes, then move into the next sections. I'll remind everybody, but when we come up to Thursday, the 10th, that's going to be another student-led review day. So come prepared with questions. We could take the whole day if necessary, and we'll just review for the upcoming exam too. Have a great weekend, folks. Try not to work too hard, and I'll see you all next Monday. Hey.
The Zoom thing.
Yeah.
I don't know, just open that and then it says like.
It looks like it's doing something. Your calculator's computing something.
It takes a minute.
Oh.
Because,
Oh,
yeah.
can I take a look at your calculator?
I don't know.
Syntax. That's interesting. Sometimes if you hit go to, it can help.
Okay,
And it says it must be this equation that's throwing it off.
okay.
So let's delete this out. And let's delete that one as well by doing that. And let's now go zoom stat. And this time it didn't do the same thing. Let's go back here, and take a look at the data. So we've got, this could be the issue.
Just do like the L, I just put the ones together, so I'll just take
Yeah.
L2 and L3.
Gotcha. But when we go to the zoom stat, it's using always L1 and L2. So I think that's what the problem is. So your L1 is, oh dear.
Yeah.
There's always a way to bring it back. If you
Okay.
don't mind, I could show you how that goes.
Completely.
So go stat, set up editor, and did something, go back to stat, edit, and there's your L1, L2.
Okay.
So let's see here. Yeah, the reason it wasn't plotting is L1 is longer than L2.
Okay.
So it should be
Okay.
working out for you
Thank
now.
so much.
You bet. Any questions? Oh, awesome. Thank you.
I should probably just one. And there was a red and red for yesterday.